Multiplexers are used in many digital systems. And up to this point, we have seen how to describe a 2-to-1 multiplexers in Verilog using structural modeling. Specifically, we use gate level modeling using the AND gate, the OR gate, and the NOT gate connected together to describe this logic diagram to implement that 2-to-1 multiplexer. I've also shown you how to use data flow modeling with continuous assignment to describe this particular 2-to-1 multiplexers, and I also went briefly through behavioral modeling to describe it. So in this video and the module in general, I'm going to dig deeper into behavioral modeling and explore more details about the different statements and the different constructs within Verilog that allows us to describe this multiplexers and other combinational circuit building blocks. Specifically, I'll talk about if statement, case statement, and for loops, and I'm going to dig deeper into what do they actually infer in terms of hardware. So let's go to Vivado and start coding. So I have opened up a new file or a new module, and I called it mux_2-to-1, and I called it _nbit because eventually I'm going to parameterize it or make it generic. But for now, we're going to start by describing this simple 2-to-1 multiplexers as a 1-bit version, and then we'll expand this code a little bit. So first of all, I need to specify my inputs and outputs, and according to this particular graphic symbol, I know that I have 3 inputs. Specifically, I have an input, and that's W0, W1, and I have another input, and that's the selector S, and it's also a single bit, and I have an output, which is also a single bit here, and I called it F. And of course, we can go ahead and describe it using data flow modeling or gate level modeling. But what I want to do right now is I want to remind you that Verilog comes with a bunch of operators. We have explored some of them, but now I want to just focus on the condition or conditioning operator, which is the one here at the very bottom. Okay, and the condition operator is really useful and easy to use. So let me show you how you can describe a 2-to-1 multiplexer using it. So according to this, what we need to do is we need to assign F equals, and the operator actually comes in a couple of things, which is basically A, question mark B, and then C in here. And I'll fill what A and B and C are. Okay, so the very first thing is I'm going to take a look, and I know what a multiplexer does. The multiplexer implements this particular truth table. So the way we do it is by asking what's the A is actually the question. That's why it's followed by a question mark. What's the status of S? Is it asserted or not asserted? If it is asserted, you're going to implement B. And specifically in here, according to this truth table, it's telling me if S is asserted or it's 1, you should return W1. Otherwise, which is the false case, you're going to have to return W0. And this continuous assignment or this particular operator will actually does exactly what it says. It will ask what S is and return either W1 or W0. And based on this value, I'm going to assign it to F. And at this point, I have used continuous assignment to implement that 2-to-1 multiplexer. So as you see, this operator is really easy to use. And frankly speaking, whenever you need a multiplexer or a quick 2-to-1 multiplexer or something like that, I usually go to this particular operator and use it. Meaning, if I have like a bigger system that at the very end of the system, I need a multiplexer to directly output somehow, I just use this particular multiplexer. It can also work on the inputs if you just want to select one of the inputs to the whole system. So instead of just me instantiating and creating a separate multiplexer, I can just use the operator. Okay, so that's good. And this operator is not restricted to data flow modeling. So far, this isn't behavioral modeling. This is data flow modeling. As it turns out, you can use all of these operators that you see in here. You can actually use them within an always statement in a behavioral mode. So what is an always statement? As a quick reminder, an always statement is actually something that it's a block. So you usually start with begin and end in here, and you place your code in between them. Okay, and the always statement usually is activated or executed whenever something happens, and that something is a change in certain parameters. And these parameters is what we call the sensitivity list. Generally speaking, the sensitivity list would be connected to some sort of an input. I'll figure out what these inputs are. And actually, by taking a look at here, I want it to execute if W0 is changed, W1 is changed, or S is changed. These are the inputs. So all I have to do is just write them. Okay. And if there's any change in any one of these, it will actually start executing. All right. So what can I do in here? Well, I can take the same exact statement in here. I'll just cut it and paste it in here. Okay. With the proper indentation. But of course, because I'm within the always statement at this point, I do not need this assign. The assign is only used for continuous assignment, which are outside the always statement. So now we don't call it continuous assignment anymore. We call it procedural assignment because it is within an always statement. And we don't call it continuous assignment because it's not continuously being evaluated. It only gets evaluated when the always statement here gets activated. Basically, I'm saying if W0, W1, or S change, this always will get activated. This particular statement will be activated too. But of course, because we are within an always statement now and we're assigning an F over there, we're going to have to tell it that this F is actually of type reg or register, because this is how it's a historic reason why we use it. It's a register. There's no memory element here. This is a combinational circuit. We shouldn't expect to see a register or any memory element, but this is how Verilog works. In general, if you see something that you want to use as an output within an always statement and you're assigning something to it, you just define it as type reg, whether it's part of the output or input, or maybe sometimes you actually can do it here. But anyway, what I wanted to show you is this particular operator, which is a conditioning operator, can actually be used in behavioral mode. And now we started with behavioral mode. So that's good. Well, according to the name of this module, I was planning to use it as an n-bit, and meaning I wanted it's still going to be a 2-to-1, but each one of the inputs and output will have a specific number of bits. And the way we do it is simply by parameterizing it. So I'm going to do this here, and I'm going to say I have a parameter, and that parameter I'm going to say, well, parameter. Okay, or maybe I should just use this here, okay? N equals, like by default, I want it to be 3, and of course I need to change all the inputs and outputs. For example, I can say n minus 1 to 0, okay? And the output has to change as well, and the output has to be from n minus 1, okay, to 0. So basically I vectorized it and I used it, and now it's a little bit on the generic side. It's a 2-to-1 multiplexer using the same operator. I don't have to change anything in it. So this is how useful this operator is. If you need something quick and dirty, like a 2-to-1 multiplexer, you can just use that. All right, well, this is good. So let's dig deeper and develop something bigger. So we have seen that we can use or utilize or develop a 4-to-1 multiplexer either by figuring out, like a 4-to-1 multiplexer takes 4 inputs and gives me 1 output based on a selector that is 2 bits, of course. And here's the truth table. And frankly speaking, we have seen that we can definitely develop this 4-to-1 multiplexer using just gate level modeling, implementing this particular logic diagram, or maybe instantiating, like taking this 2-to-1 multiplexer in here and instantiating 3 of them and connecting them and doing it. However, what if I wanted something a little bit bigger, like 16-to-1 or 32-to-1 or something a little bit bigger? So this model of instantiation or something becomes a little bit on the tedious side. And here comes behavioral modeling, and it will make our life a little bit easier. So let's go and develop a 4-to-1 multiplexer. So I'm going to go in here. I created another file in here, and I called it multiplexer 4-to-1, and I also called it its n-bit. Okay, so we're gonna develop now a 4-to-1 multiplexer. So in a 4-to-1 multiplexer, of course, I need to specify my inputs and outputs. As usual, I take a look at the diagram. I know I have 4 inputs, so I'm going to just say I have an input, and I have W0, W1, W2, W3. These are my inputs. And of course, I will have inputs as S, and because I have a 4-to-1, so S has to be a 2-bit one. It's like you can't not have it as 2 bits. Okay, and the output will be, because I know I'm going to be using behavioral modeling in general, so I can just use reg right away, or I can just leave it. Usually I leave it till I need it. Okay, so we can just do this, and that's it. And like we did with the 2-to-1 multiplexer, to make it a little bit more parameterized or generic, I don't care how many bits is each one of them. All I care about is that F will be connected directly to W1, W2, or W3, or even W0. And they have to be of the same size. So to parameterize it and make it a little bit multi-bit, for example, we can just say here, and you can say parameter, okay? And that parameter will be n. I'm going to call it 3. All right, and then we can specify now this is of size n minus 1 to 0. That makes it 4 bits, and then n minus 1 to 0. That also makes it another 4 bits. Frankly speaking, 4 bits is by default only. Okay, it's not necessarily like when you instantiate this one here, you can specify n to be whatever you want. All right. So let's get started. So the very first thing we can say, well, can I use that data flow modeling or the condition operator to do this? And the answer is yes. And you can use it in continuous assignment or procedural assignment. But because I am focused at this point at behavioral modeling, so I'm just going to use it with an always. So I'm going to say always, and the inputs usually are W0, W1, W2, W3. If there's any change in the inputs or the selector, that's S, I need the always statement to actually get executed. Okay, so that's perfect. Good. So now what can we do? Well, let's do that assignment in here. And since again, I'm gonna specify that this one's of type reg, because I'm gonna say f equals, and here's what you can do. You can definitely take a look down here at the S1 and S2 and describe it. For example, you can tell me, well, let's ask what the value of S1 is. Okay, if it is something, we'll do something, and if it's something else, we'll do something else. Okay, all right, so let's assume that S1 is true. So this one here, I'm looking at the diagram right here. So if S1 is true, which is this one in here, it will activate W2 and W3. So technically, I want to either route W1 or W2, and you can actually see it from here as well. So if S1 is actually active, that means, or high, that means you want this one in here, so you're either routing W2 or W3. But how do you know which one to route at this point? Well, you're gonna have to ask what S0 value is, because you want to know this. And of course, if it's not the case, basically if S1 is not the case in here, you're gonna go to the else statement and you'll be routing W0 or W1, and again, it's based on the S0. What I'm trying to say in here is, like, you ask the first question, which is S1, and as it turns out that this operator, or the condition operator, you can put other condition operators within it. Okay, so in here I can say, well, if it is true, that means I am actually, if S1 is true or high, that means I am actually routing this, but it's based on the value of S0. So you can technically do another condition operator here, and you can ask what is the value of S0, and if it's true, if it is true, probably I need to route W2, and if it's false, I want to write route W3. Okay, or actually it's the opposite. So if it's active, that means it's S1 is 1 and S0 is 1. That means I want W3 to be routed, and that's exactly what I can see in here as well. Okay, so we're going to do W3 in here and W2 in here. And of course, I can do the same exact thing. I can put another condition operator in here, S0, question mark, and then I can say W, probably 1. Other than that, it's W0. All right? And that should implement the 4-to-1 multiplexer, and it's a generic version of it that can be, like, the inputs and the outputs can be n bits. So in this particular case, they're 3 bits by default. Okay, so that's good. So definitely I can use the condition operator. So I'm showing you here how useful it is. However, I might have lost some of you in here. You didn't follow what exactly I'd done in here, because this is not really readable or easy to read. So a better way to do it is, instead of doing that and using the operator, we can use other behavioral modeling constructs. Specifically, I'm going to start by saying, okay, let's use an if statement, for example, okay, and or let me call it if else at this point, okay? So what do I mean? Well, gonna try to implement the 4-to-1 multiplexer by describing its behavioral, not by describing its structure. Describing the behavioral tells me, okay, let's take a look at this particular truth table in here and describe it. So how do I describe it? Well, I'm going to say, okay, if, and let me just see this here, S equals, and I'm going to say it's 2-bit 0, 0. Okay, what do I want it to do? Well, I want it to do specifically to write that F equals W0. That's what I want. Okay, that's good. What can I do? Well, it's kind of like C. Definitely, we're not writing C code in here, so things are different. But I mean, the syntax looks the same. So we can say else if, and you can say, well, S is 2-bit and binary. Let's describe it with 0, 1. So what do I want in this particular case? I want F to be equal to W1. And of course, I can say, okay, else if, I called it is in here, but that should be if, okay, and then S equals 2-bit 1, 0. Okay, and what do I want F to be? F equals W2. Okay, and lastly, you can definitely use an else, but I'm just going to say, for the sake of completeness, I'm just going to say else if S equals, and all of these should be equal, because I'm actually asking a question. This is a logical expression, not an assignment, or it shouldn't be an assignment. Okay, and you can say F equals W3. And hopefully this is a lot more readable than this particular data flow modeling here or the condition operator. They're doing exactly or almost the same exact thing, okay? But here it's much, much clearer. I can just say, like, based on the value of S, I can do whatever I want. And generally speaking, for the sake of completeness, I would tell you, for reasons you're going to see shortly, include an else statement all the time and specify what F should be. And you can, for example, say, well, I want it to be, for example, let's not specify the number of bits, because usually I don't know how many bits. It's n bits, okay? You can just, according to how we specify numbers in Verilog, you can just say, I don't know how many bits, but I want to specify it in binary, and I specifically want to say that it's X, which is X is I don't care. What I'm saying is, in here I counted for all values of S, okay? And if none of them happens, which is supposedly not the case, I mean, I'm going to say, well, I don't know what f should be. Okay, there's probably a problem in here if you see the x. Okay, so you can definitely go and see this here, and you can go open the elaborate design just to see what actually gets inferred in here, and hopefully it will infer a multiplexer, a 41 multiplexer. Okay. And yes, exactly as we expected. It's actually implementing it using 2-to-1 multiplexer, 2-to-1 multiplexer, 2-to-1 multiplexer, 3 2-to-1 multiplexers, kind of similar to what we did before. So yes, it does implement it. So this RDL analysis, just as a reminder, it just goes through your code and try to interpret it pretty quickly without actually going through the synthesis and implementation, and tries to tell me what it thinks my code should implement. And I think it's correct at this point. Of course, I mean, the best way to do it is actually to create it, or to test your code if it's working or not, is to implement it using a test bench. And that's exactly what I did in here. I basically wrote some sort of a test bench. You can just go ahead and run the behavioral simulation just to see if it's actually working or not. And you can go ahead and just read what I did, but as usual, I just followed the steps of creating a test bench to see it. So we're going to do this here. We expanded a little bit, and just to make sure everything is working. So what I did is I specified 3, 5, and 7, and 11 in terms of the W's. Okay, W0 to W1, and based on the selector. So in here, I selected 0. That means I want W0 to be routed to the output. In here, I selected 1. That means I want 5 to be routed to the output. That's F in here. And in here, I want the second one, which is 7, to be routed. And that's exactly what happened. And then 11, and it got routed exactly as I expected it to do. And you could read the rest of the test bench in here just to see what's happening. So frankly speaking, what I did is I just made sure that the selector is number 3. And you just need to see that it's actually outputting whatever is on W3 should be on the F. And that's exactly what I see. I see 11, and then when it changes to 10, it changes, and it doesn't care what's happening to the other W's in here. Okay, so it is working exactly as we expected it to do. Okay, let's go ahead and see if there are other ways to describe that end-to-one multiplexer. So I'm going to just close that in here, the test bench, and just make sure you make them your top file before executing all of these. All right, so that's good. So what we did in here is we saw how to describe the if or the 4-to-1 multiplexer. It's a generic version with n bit basically, which is in this by default is 3. Okay, using an if else and using the continuous assignment with the condition operator. Okay, so let me show you another way to do it. So you can do this here, okay? And another way to do it is using case statements. So in a case statement, all you have to do is just tell me, okay, similar to an if statement, you can say case of S, okay? And then in here, I usually end it with an end case right away. And then in here, I'm going to say what type of cases or what type of values can S take. It can take 2-bit 00, okay? Or it can take 2-bit 01, or it can take 2 bits or 2 bits binary 10, okay, or 2 bits binary 11, okay? And these are the cases that I have, and all I have to do is just replicate whatever this F here, F equals W0, and the one down here, F equals W1. And if you have more statements within each of the cases or each of the matches, you're gonna have to put a begin and end. But because I only have one, I don't need to do this at this point, okay? Or because I only have one statement in here, okay? All right, so and the last one in here is F equals W3, okay? And of course, because it's a good habit and for reasons you're gonna see shortly, you should use a default in here, okay? And in the default, what I'm gonna say is, say B is X. And X's usually don't know or don't care, okay? What I'm saying in here, if S is not one of these cases, that means there's something wrong. I don't know what F should be, or like, so I'm just gonna specify it to X. And usually in test benches, you'll see it, or like when you're testing something and you get an X, that means there's something wrong with your code. In here, they're getting that there's something wrong that is happening. So you can save this in here, and of course, because I'm within the elaborate design in here, I can just say reload, and I'll create a new schematic using this, and I'll see if it's actually implementing a 4-to-1 multiplexer. I believe in this particular case, it will implement a complete 4-to-1 multiplexer. It's not going to do it in stages. Let me just see. Yes, it actually did not do it as stages, and that's actually on purpose, and I knew that exactly, and I'll tell you why in a minute. But or I'm going to tell you in a different video what's happening in here. But it actually implemented a 4-to-1 multiplexer, and you can run the test bench in here, and you will see that it actually is performing in exactly the same way without me changing anything in the simulation or the test bench. It's actually the same exact test bench. Nothing has changed in here. So let's do that in here, and I'm going to see that. Let's do it, and you'll see it's exactly the same test bench. Nothing has changed. I just changed the way I wrote the code, and the code inferred a little bit of a different hardware, but it's actually functioning in exactly the same way. Okay, so now I want to show you a different construct within Verilog. So I showed you the if statement and the for loop, or the if statement and the case statement. Now I want to show you for loops. And the way I'm going to do it is by describing a generic 1-bit multiplexer this time. And what I mean by a generic 1-bit multiplexer, that means now what I'm going to generalize or parameterize is actually the number of inputs. So I'll have multiple inputs in here, and I don't know how many of them. I can actually specify, and let's say that the number this time n represent the number of inputs. I can just write it as ins just so that you don't get confused. Okay, ins is the number of inputs. But at this particular point, I'm going to assume that each one of these inputs is exactly 1 bit. So this one here is 1 bit, and the other ones here are also 1 bit, and it will be routing it as 1 bit. And of course, the number of bits here is actually based on the number of ins. Specifically, it will be related to the log base 2 of that ins, that parameter. Okay, so if I have, for example, the ins, which are the number of inputs in here is 4. Well, I know if I have 4, I need log base 2 of 4, that will be 2. If I have 5 inputs, for example, in here, log base 2 of 5, it's going to be 2 point something. So what I'm going to do is I'm going to take the ceiling of that. Okay, this is the indication of a ceiling. So log base 2 of 5 ceiling hopefully will give me that number. Let me just write that here. Log base 2 of 5, it's going to give me a non-integer number, but that non-integer number is definitely greater than 2, so hopefully I'll get 3, and that's what I'm hoping for. And of course, if I have 5 inputs in here, I need at least 3 selectors to choose between them. Of course, there are some cases that I'm not going to use. But anyway, that's the case, and we're going to be using this particular equation in that generic code, so let me show you how we can do it. So first, what I'm going to do is I will create that parameter in here. I'm going to say that parameter, which is, I'm going to say parameter in here. Okay, and I'm going to call it ins, which is the number of inputs, and let's say it's 4. Okay, for the sake of argument, it's 4, or you can set it to 5 if you choose, like we did right now. Okay, and then we can say, well, I have an input, and the number of inputs in here, you can say W0, 1, 2, 3, all the way to 4, because I have 5 of them, or I'm going to vectorize them. Remember, each one of these inputs is exactly a single bit at this point. Okay, so I'm going to, well, instead of n, I called it ins. Okay, I'm going to say -1, I'm going to call it 0, and that will be W. These are the inputs. So each one of these W0 will be W, my first input, W1 will be my second input, third input, and fourth input, and so forth. Now, what I need to do is I need to figure out how to do the selector. I know for sure it has to be vectorized in here, and the least significant bit to be 0, but the most significant bit is actually something to do with the number of inputs in here. Of course, I can pass it as another parameter. For example, I can say here selector in n, and I can figure out by hand that this should be 8 or something like this. Okay, but as it turns out, that Verilog actually allows me to use something we call system functions, and system functions usually start with something like a $sign in here, and then you can call that system function whatever it is. System functions has nothing to do with the hardware implemented. I'll explain this once I finish the code. But for now, what I know I need is actually log base 2. Specifically, I need the ceiling of that log base 2 of a certain number, and that number is actually the ins. What this will give me is the following. It will give me C log base 2 of ins. This is basically 5. It will take that 5, will compute the log base 2, the ceiling of it, which we computed to be 3. I don't need from 0 to 3. I need it from 0 to 2 because I need 3 bits only, so I'm going to have to do -1 in here. And that's that particular input. And of course, I need an output, and that output is a single bit. And because I'm using behavioral modeling, I'm just going to, ahead of time, I'm going to tell you that we need a register in here for the F. And of course, let's go and write that code in here. What I just did is I just described my inputs and outputs. Now we go through the code. And the code is as simple as we, well, it's not as simple, but at least for the always statement, I can just say, well, I need an always, and I usually say begin and an end. Let's figure out what the sensitivity list is. The sensitivity list depends on the input, so if any of the W's or the selector change, I need this to execute. And what am I doing through it? Well, I will actually have to figure out how to do the F. And in this particular example, I decided to generalize it or parameterize the multiplexer in this particular way so that I can show you a for loop. And as it turns out, that we need a for loop in here because it's parameterized. I don't know how many inputs. I'm going to go through all the inputs, okay, from k equals 0. K is less than ins, okay? Specifically, basically, I'm going to input 0, input 1. Let me show you on the diagram in here. So I'm going to go input 0, input 1, input 2, input 3, input 4. I'm just going to pass them one by one. Frankly speaking, we're not doing this sequentially because this is not C code. Everything will be interpreted into hardware. but this is what the behavior that I want it to do. Okay, and of course I need k plus 1, and of course because k is actually some sort of a number, we're going to have to figure out what it is, and generally speaking you need to use integer. Probably you have seen it in a generate for loop. This is not a generate for loop, this is not structural, this is actually behavioral, so you're going to have to specify it as an integer. You cannot use gen var k in here because this is within an always statement, not within a generate and generate. Okay, so we're going to do this in here, and inside it what I'm going to do, let me explain to you what I'm doing in here. I'm going to the first input in here. I'm going to say, hey input, your number is 0, is it the same number that is on the selector? Okay, so I'm going to have to ask, is that number that I'm currently at the same as the number that is specified at the selector in here? If it is the same, I want that output or that input to be routed to the output. So all I have to do is just say f equals specifically that particular input. And that's basically it. So I'm going to actually just like, let's take a look at it again. So what this for loop and the if statement is doing is the following. Go into the first one. Is it the same one as the selector? No. So it's just going to ignore that for loop and just go to the next iteration. Here, is it the same as that one here? Well, let's assume that it is. So all I have to do is just basically route it out, and that's it. And I'm done. And that's how this should work. So now if I actually save this, I'm going to take a look at it. It should work properly. So let's see the schematics in here to see what's actually inferring. And again, these are actually 5. Again, everything here is not sequential. This is actually interpreting it as hardware. So I'm expecting to see a few multiplexers, and that's what we did. Frankly speaking, there's actually a problem in here, which is an RDL latch in here. This is actually, a latch is a memory element. We're going to talk about it in the next video, that you should not have a storage element within it. And I will solve it briefly in here, and I'll explain to you how I'm solving it this way and why am I solving it this way. But frankly speaking, all I have to do is just say, okay, let's say that f equals, I'm going to give it the default value of x, which we don't know. We're going to save it in here. We're going to reload, and you're going to see that we're going to get rid of that latch. What I'm doing in here with the f equals bx is I'm going to tell it, like, by default, give it that unless I change it. That's what I'm doing. So what I'm doing in here is I'm ignoring that one here, and now the schematic is correct. It's actually a few here. So it's actually 1, 2, 3, and 4 specifically. Okay, so 4 of them. So of course, if I actually change that default value to say, let's say 6, I'm going to see that by doing the reload in here, it'll actually do something a little bit different, or it will interpret it by default. Remember, this is generic, so you can actually change that. You can change it as much as you want when you instantiate it. So we're going to do this here. We'll wait a second, and then we're going to go to the schematics in here, and the schematic just probably added another 1, 2, 3, 4, and 5, and there's no latch in here whatsoever. Okay, so that's good. Again, it's important, like this line in here, which I'm going to explain in a separate video, it's important like to understand that everything you're doing here gets interpreted into hardware. It's not being executed sequentially like C. All right, but really the true test is in here is using a test bench. So I went ahead and I wrote a test bench, and you can actually just go and run this test bench. We're going to just take a look at it quickly just to see how it's actually doing. So you can read the test bench and what I did, but basically I instantiated it with a certain number of bits. Let me see how many bits. I said that ends is actually 4, and I just did it that way. Okay, and then you can do this in here and you see it. Let's expand that a little bit in here. What this tells me is I have a W, I have that, and frankly speaking, that W, I need it to be in binary because that's what I care about. So you can go in here and you can tell me the radix is binary that. Okay, now I know that it's this much, and the selector is actually 0, so I know that the F should be whatever is on 0, which is 0 in here. And then 1, which is that 1 in here, and then 2, which is that 0 in here, and then 3, which is this one in here is that. And then I kept it at 3, and then I started changing it, and frankly speaking, just mapping that 0, this is a 0, this is a 0, and this is a 1 in here, and that's exactly what I see. So it's kind of working exactly how I expected it to do. Okay, so just to briefly mention about being generic multiplex. We have designed a generic multiplexers in a couple of ways. So when I say generic multiplexers, there's a couple of things that you need to pay attention to. First of all, the number of bits for each one of the inputs. Okay, second of all, the number of inputs in total in here. Okay, so there are a couple of parameters. Now, I haven't designed a truly generic multiplexers in here because it's a little bit more involved in Verilog. So because if I'm actually generalizing that number of inputs in here or number of inputs, I need to figure out a way to actually make each one of the inputs as multi-bit. If you think about it, I will be thinking about inputs as two-dimensional arrays, and it's not supported in Verilog readily available to actually get an input. Like for example, when you say an input is actually some x, and that x is actually you can say a one directional vector, or w, we called it the input, and you can do another one which is actually infer memory. But Verilog doesn't support it to be this as ports of inputs and output. However, system Verilog allows it to. Anyway, what I'm trying to say is there's a couple of ways to generalize these multiplexers. You can either generalize or parameterize the number of bits in each one of these inputs, which we have seen in the multiplexer, the 4-to-1, and probably the 2-to-1 as well. I showed it to you in the 2-to-1. And the other one that I just showed you in here is actually the number of inputs together. It is really interesting, and I encourage you to look into it, like how would you really truly create a generic multiplexer.